we will start from basics. And from basics, I mean Hooke's law. Hooke's law is pretty much the core of elasticity theory. Do you know Hooke's law?
Stress is direction of the strength. Is that?
No. The words are too complicated, stress and strain, because we will start from force and displacement. So, simple things. There are a few slides in the second lecture, the second set of slides that I prepared. One additional thing, all the PDF of the lectures are already available in a site that is an ICTP website. It's a sort of a Moodle website. But up to now, I don't have access. So I will tell you as soon as possible where to go and how to find the PDF of the lectures. Now, what else? Let me try if this is better. Because we change. Better?
Yes.
No, you're going to sleep. So let's try it. And I'm going to sleep as well. That's not nice. Okay. Wave physics is really, I think, that's my opinion, the simplest course of this diploma, Earth System Physics, whole course. And really, I would like to start from this question here. It is a very simple one. This room is full of waves. What do you think? Can you tell me some waves that are in this room?
Sound waves.
That's your problem because I'm speaking. There is some noise. We can study also the Green's function, this like that. It's the response of the system to an impulse, something like that. Okay. Sound. What's next?
Light.
Light. Right. What's next?
Vibration.
Which one?
As a result of the sound from.
Well, since we are not at 0 Kelvin, there is some vibration. Temperature. Okay, something is vibrating here, luckily. What else? What about the radio waves? They are here, but we don't feel them. Infrared waves? Yes. Yep. Okay. So it's really full of waves here. Some EM waves that we cannot touch, they're not mechanical waves, and some mechanical ones, like sound. But what is a wave? Well, you know, at the end of these 4 slides, it's a very small set, it is a sort of a prequel of the course, there is an equation. It is wave equation. So maybe you can answer, well, let's do this. We're going to build this one. So you can see, is this a wave? No, it's not. What is this? Well, it's terrible writing. It's a partial differential equation of a second order in 2 variables, linear. Nice. And we do know the solution. Maybe. But we're going to build this one. And one could say, wait a second, we can use here, something like that. And now everything is relaxed. Wait a second. Why we can build this equation? Why we consider this as a solution? This is the simplest, but it's not the only one. It's a plain harmonic wave with a single frequency. We're going to build this, okay? So we're going to revisit what we can call a wave. But this is a mathematical description of a wave. What is physically a wave? You said sound. That's a wave. What about heat? Is it a wave? Maybe if you scratch in your background and you try to remember some heat equation. It's not that one.
Yeah.
Yeah, please. You're totally free to speak and to...
Wave is a disturbance that can travel in a medium or not. Even
Yes or no?
yes,
So
it
it's
can travel
traveling.
in medium, in matter, or in space. So that's a disturbance. And
Okay, space and time. You said matter, but the light can travel into vacuum.
yes, matter and in vacuum.
Okay, for mechanical waves, that is the main topic of this course, we need a medium. Good. But what about heat? It's traveling
Yes.
in a medium. You can take the example of the iron bar, you can take a heater, and in some time, temperature will rise everywhere. So it's traveling.
Conduction.
That's conduction. Or we can take irradiation. We can take convection. But is heat transfer a wave? No, because it's not obeying this kind of equation here. Something is different. Because diffusion equation is not considering the second derivative respect to time. Do you remember, and we are going to build this equation, why there is a second derivative here? For today, we're not going to speak about waves, but about vibrations. Now, what is mechanically a vibration? Let's see if I have, yes. Still my lab here. Okay, yes, I do look very silly. Is that a vibration? Oh, yes. What do we need to build this tool here? Well, we need something, some extension, it's not necessary. What do we need to build a pendulum?
Need resist support.
Pardon?
Strain.
A mass.
Strain,
Mass.
mass,
Power.
but in empty space there is no vibration like that because we need gravity. So we need a restoring force.
Yeah.
Otherwise we can move it and it's going to stay there. For example, if I put on this table here, it's not oscillating. I can move it, but it's not trying to go back, right? But here it's trying to go back. So we need a restoring force. Now, and this is going to be one of the last slides for today. We have 2 blocks today because we realized that your day is empty. So we decided to put 2 lectures today. Okay, what if I start from this initial configuration? Would you call it a pendulum?
No.
No, you could say large angles.
Yeah.
You do remember something. Why they are not nice?
Because to be the pendulum, there must be sine theta must be equals nearly equals to theta.
Must be. You're right. That's the answer. Because when we are going to write the equation for a pendulum, forget about this. We will say something like that. Because otherwise we cannot build a linear differential equation. And we are in the mess. Because we cannot solve differential equations using this. So the shortcut is to say, okay, come on, I'm lazy. So let's stay for small angles. This is pretty much true. Let's go. And we have a vibration. A periodic vibration. And we can measure time. Well, sooner or later it's going to stop. Why?
Because of the air resistance.
One, then
Um,
there is some friction here.
yeah.
So, sooner or later, it's going to stop. It's damped. So we have a damped vibration. So trying to sum up to now. To build a wave system, we need a vibration. Additional, silly question. Is this a wave? Would you call it a wave?
Yes.
Why? What is going the energy? Oops. Energy is staying here. We have our universe here. It's one point. Well, it's not a point. It's a bar. But we can imagine to consider the center of mass, and we have one point. We just need one coordinate. So actually, we don't need this. Time is enough. So it's not a wave. It's the beginning, could be the beginning of a wave. But to build a wave system like this, we need to start from something that is going to have a stable equilibrium. Because, for example, I can do also this. I can move it, but I'm not going to do that. But it's not going to stay there. It's not going to vibrate here. That's an unstable equilibrium. So this is nice. So it's a matter of potential. So, to sum up, to build a periodic vibration that is going to be a brick of a wave wall, we need small perturbations of a linear restoring force. So what? The next step, I can use this. Now we do have a linear restoring force. In the next set of slides, we're going to speak about really high school physics. We're going to use Hooke's law. It's beautiful. It's been a conqueror, let's say 300 years ago. It's not a trivial one, but it's so nice because we have force, we have displacement, and we have a constant. Now, as soon as you couple this with Newton, that's acceleration. The dynamics are there. And actually, that acceleration is the one that we have here. So for a classical system, and we're going to deal just with classical systems in this course, what is important is to find the dynamics of motion, and that's Sir Isaac Newton. That was not a good friend of Robert Hooke, but that's life of British important people. Okay, Newton, Hooke, and now we do have something like that. And we like it. It's a linear differential equation of a second order in one variable. Just one. Which one? X. Now, as soon as we build this, and it's linear, and it is restoring, because if we put a plus there, the system is not going to vibrate. It's going to blow up. So linear, restoring, minus force. With Newton, then we can build what we can call, it's working, an harmonic oscillation. Harmonic oscillation in principle is characterized by two, well, let's say, first feature is periodic. Second, what about the energy? Well, the energy is going to be conserved. And now we have two kind of energies in this system here. One is the kinetic energy, because when we have motion, we have kinetic energy. And it is proportional to the square of the velocity, we know. And in this case, to mass. Mass square of the velocity, 1/2. But in the case of the spring and the mass without friction, well, we do have potential energy. Which one? The spring one. Because when we pull, okay, we want to go back. And we have a continuous balance between kinetic and potential. 1/2 m to the square v times the square of the velocity. 1/2,
Key times x.
okay, the square of the displacement. And it's a continuous balance. Maximum potential, maximum kinetic, maximum potential, forever. Really forever? Any real system actually has some damping. So part of the energy will flow out of the system by many ways. For example, friction of the air. For example, friction of the table. And you're going to discuss friction about earthquakes. In these days, there is a workshop. The local coordinator is Karim Abdia. It is about earthquake dynamics and fault systems. Well, friction is there, definitely. If no friction, the exchange will last forever. Back and forth, forever. It's really boring. Because the plot is that one. Okay, what we're going to do next is to study vibrations, linear differential equations like that. Well, actually we did it. Energy considerations, balance of energy, damping, and then we're going to consider also one additional feature. For example, we have a system, small angles, because I'm lazy, okay? Starting initial condition, because remember, it's a second order linear differential operator. We need to define two constants of motion. Which one? Well, position and velocity at the beginning. Good. What if I'm going to, not to just to displace or to give some speed, but what if I'm going to force it? I know that I'm looking very silly now, but I'm forcing it. And I can force it very slowly or very fast. And if I'm forcing it very fast, it's not able to follow. If I'm forcing it very slowly, it's following. But if I'm forcing it at a specific frequency, wow. If I combine the frequency of the excitation with the natural frequency of the system, is this one, well, it's going to absorb a lot of energy. It's called resonance. Maybe we want it, maybe we don't. For example, if you are designing a shock absorber, we don't want resonance. So, what we're going to do today, I guess, is to consider harmonic oscillators, energy, damping at a very soft level, and forcing. Okay, and with this, we can also begin to build more complicated systems, like this one. This is an example of an interatomic potential. Very simple. You can call it Lennard-Jones potential, but what is important is that you're putting together two forces of nature, the economic one, it's going to attract, the repulsive one, we can go to quantum physics. You put them together, and that's the potential. Now, what do we see here? Well, we see that there is a minimum in the potential. And when the potential is not flat, when the potential is not showing a hill, but it's showing a valley, we have a stable equilibrium. Every time. It's like to have a ball, and you make it roll, it's trying to go back to the center of the minimum. So we have an equilibrium place here, and it's a stable one. Now, for lazy people like myself, what we can do is to take whatever function there, to use Taylor's formula, and to stop at some level. So you have a constant, who cares? You have the first derivative, no, it's a minimum, it's 0. Then you have the second derivative. And if you approximate that curve around the equilibrium here, with a parabolic expression, then you have the potential that is like 1/2 kx squared. And if you have an harmonic potential and you compute the force, that is minus the gradient, you get this. So you can say, that we need a linear restoring force or an harmonic potential with a minimum, not a maximum. So you see, it's the same. Okay, what's next? This is not a wave. This is an harmonic oscillation. To build a wave system, we need to let the energy to flow in time. Fine, it's already here, but also in space. And to make it flow in space, we need to couple harmonic oscillators. And this is what we're going to do. For example, we can imagine to have two of these. I'm going to show an Amplitude. Yes?
Question in the previous slide.
Wow. You're not supposed to have questions about this. It's too simple. This is just a prequel, by the way.
So in that plot, is that plot inside the Coulombic region or something else?
It's a combination. It depends on these two shapes. You have to combine them.
But if there are one electron and proton,
This is interatomic.
oh, sorry, thanks.
Your question is for solid state physics. We're going to make a small tour into solid state physics, but it will not be solid state physics. And we're going to do that exactly coupling oscillators. Now let's imagine not protons and electrons, but just atoms. And you can imagine to connect them with springs. So it's a mechanical equivalent of a lattice, of a monatomic lattice. Now you can imagine that if you move one, if you give energy to one of the oscillators, if it is coupled with other ones, that energy will try to flow. For example, okay, let me start. When you will have access to the website, you will see that there is a syllabus also with some links to very simple. I hope that the web, oh, if my account is not online, I'm not sure that this is working. Let's see. Well, the one is working. This is not working, but there should be a page here, and it is this. We need some time to. Let me try to do something else. This is a prequel. Let's put 10 and 10. Okay. Yeah, you should tell. Okay, that's the card that I was missing. Sorry. Good. Now you would say, what the hell is this? We're supposed to take a diploma course, not this one. Now, this very simple system actually is containing many important features. Now, let's think about the spring. With this configuration, the spring is not active, because actually the mutual position of the two pendula is letting it quiet and not working, right? Okay. Let's try to do another one. Let me put here a minus. Well, now, at every instant of time, the spring is working. And it's adding a restoring force. Because we have a pendulum that is under the action of a, for example, gravitational potential, trying to go back to the equilibrium. But now it's coupled with another one. So we have an additional restoring force. And actually, now the system is vibrating with the same frequency. All the points of the system, just two, are vibrating with the same frequency, with the same amplitude, but now the frequency compared to the previous one is higher because the distorting force is larger. So it's moving faster. But let's consider another initial condition. Let me put 0 here. Uh-oh. Now the two time histories are different. Because when one is reaching the maximum, the other one is 0, and vice versa. Because the energy needs some time to transfer to the other one. Let me start again. So at the beginning the energy is here, it's beginning to be transferred to the other one, and then, uh-oh, there is nothing else, so I have to go back forever. Now, wait a second, because now the system is not moving with the same amplitude. Before it was together or in opposition, but the same amplitude, same frequency. Now it's not the case. Amplitude is changing in time, maximum, minimum. Is this a wave? Not yet. But you can imagine to add a third one, a fourth one, many others, and all the energy that you can input at a specific place can flow in other places of the world. So, what I'm trying to say is that to build a wave system, we need a vibration of an oscillator that is under a stable equilibrium position, and the energy should be allowed to transfer in space. Now, question. What is deciding the rate of the flow of energy in this case here? Because you see, we need some time to go from a maximum here to a maximum here. We need some time. What is, in this very simple system, the component that is deciding the flow of energy? Well, from one place to the other, full stop, we have to go back and forth. It's the spring. Now let's imagine to take the spring and to replace it with a rigid bar. If you put a rigid bar, there is no time delay. Immediately, energy, if you move one, the other will follow. If you take the spring and you replace it with nothing, you have to wait infinite time for the energy to flow, because it will never flow. You move one, but it is uncoupled, the other will stay. Actually, the spring here is a representation of interatomic forces, or forces between elements of the system. For example, if you have studied some fluid dynamics and you have considered a very convenient approximation, because it's letting the equations to be simpler, many times you use the condition of uncompressible fluid. Okay. Uncompressible means that as soon as I push it, immediately all the system will move. What does it mean? That if I take sound, speed of sound is infinite. Because sound is exactly this. In a fluid, you can hear sound. Like whales, dolphins, and many other animals know they're using water to communicate. And so when you say that the fluid is incompressible, you're saying, okay, well look, sound speed is so fast that it is infinite, let's take it out of the game. And it's like saying, okay, the spring is rigid. It takes no time to take this information to another place. Of course, it's not physical. It's just a mathematical approximation that is convenient when you want to study something slower. What? Gravity waves, for example, not sound waves, in a fluid, in fluid mechanics, or other kind of perturbations. But the spring here is replacing that idea. Is it soft? Is it hard? Is it nothing? You can go from a spectrum of phenomena from uncoupled systems to fully coupled systems. And there is another feature that is interesting here. This system has 2 degrees of freedom because we have 2 masses. And if a spring is rigid, actually it's one body. But it's too trivial to be considered. It's a system with 2 degrees of freedom, and it has only 2 kind of motions where all the points of the system, 2, are moving with the same amplitude and with the same frequency. And those are called the normal modes of the system. And one is this, and the other one is this. They are the 2 that we have seen before. And what is funny is that since this system is linear, we can describe whatever is happening there with a linear combination of the 2 modes of the system. It's called modal analysis. You can apply it to this system here, you can apply it to the table, to a building, to the earth. That's why at the end of the course, I hope, we will be able to study the 3 modes of the earth. They are not 2. It will be a very complicated set. So for example, if I write here another initial condition, and if I start, you see now that the time histories are different, but they can be always written in terms of a linear combination of the 2 fundamental modes of the system. And that's why in the slide here I was adding this feature, because now the perturbation can travel. Well, with just 2, it can move just by 1 step. How much? It depends on the distance between the oscillators. How fast? It depends on the spring that is coupling the 2 oscillators. But we have propagation of energy in time and space. So we can build something like that. Okay, and the next step is that when you consider a system with n degrees of freedom, and if it is linear, you will be always able to study the modes of the system and to write everything that is existing in that system as a linear combination of those 2. So the third animation can be written in terms of the first 2. Of course, we will have to move from 2 to 3 to 4 to 5 to infinite. How many modes will have this bar here? Because actually the next step is to consider a set of atoms or oscillators distributed in a continuous way. Because if you don't have a continuous distribution of mass, you cannot take this derivative. Otherwise you have holes. So if I compute some quantity where I have 1 of this here, but not in the middle. So the next step is to move from a chain of atoms to a string. And what is a string? Is this a string? You know, my course is made of silly questions. Is this a string? No, it's a bar.
Yeah.
What is the difference between this and this? Well, that's pretty much a string.
This is rigid, so that is not rigid.
Okay, well, rigid is a good word. Also, if, we will see that in elasticity, rigidity is something a little bit different that is related to shear stress. But actually the technical word would be stiff. So this is stiff, but is not. Can we play a guitar made by this? No. We can play percussions with this, because it's a rigid bar. It's so stiff that we do not need to apply tension to the system to make it vibrate. But it's vibrating, like that. Okay? Now what about the string? Well, if we want to play a string, we need to apply tension. Okay? So actually, these two systems are not that different, except stiffness. What is going to decide the notes that can be played by this and this is tension that is already here, or we can apply there, and density, so the material. And we can play a string. Oh, pardon, we can play percussions or string instruments. But wait a second, because there is a fundamental step to play a guitar in a classical way, and not for string theory with 26 dimensions, is that we need to forget that the distances from atoms can be visible. So we will assume a point of view that is the classical mechanics. We will be so far, or if you want, our wavelengths will be so large compared to the interatomic distance that we can forget about the molecular and atomic nature of this bar. And so that we can write a differential equation in which spatial coordinates are continuous. That's why it's called continuum mechanics. And then we will try to study elasticity theory and to look for waves into this table, not only the sound that I produced here, but also the vibrations that are running inside this table. You can call them seismic waves. Well, it's better, table waves, but it's the same. And they will be compressional waves like sound, P waves, and shear waves. What is a shear? Well, you have to imagine that if I apply here a stress, a force, for now, laterally to this table, I'm not that strong, so I feel resistance. But if I do this in the water, in ideal water, dry water, I feel no resistance in making a cut. I feel resistance compressing water, but not cutting it. So actually, what we are going to define as S waves, they will be shear waves inside mechanical materials that are not fluids, not ideal fluids. And then what we will try will be to describe seismic waves inside Earth models, flat, spherical, until the end of a story that will be the three modes of the Earth. So that's the plot. It's a long one, but we will take many shortcuts. But the idea is to start from vibrations, to build wave systems, and then to begin the study of the Earth. To sum up this part here, when we build a system where perturbances, or let's say, how can we call a wave? Well, let's say an energy packet in some way can travel in space and time. And looking at maybe borders, can be bouncing back, propagate, and stand, like standing waves in a string. So to sum up, we can say, well, what is a wave? It's something that is a transient, that is moving in space and time with a given energy, with a given velocity, and it has to obey, it is, how to say, shaped by this equation here that is called the general form of a linear wave equation. Wait a second. That's the simplest form. Why? Because v, and we're going to call it wave velocity, will be constant. And why it's also very simple? Well, because here we have just one spatial dimension. It's nice for a bar. It's nice for a string. If you do forget about the section, it's not good for the Earth, because we will need to move into 3 spatial dimensions. So no surprise at all when we will replace the second derivative respect to space in 1 dimension with another operator that is taking care about y and z, or in spherical coordinates about radius, longitude, and latitude. That will be a Laplacian, but physically it's the same thing. So we can give a sort of an answer to what is a wave and what we're going to study here. It's something that is propagating. It's an imbalance of a lot of energy, definitely it's carrying energy, and it is organized in the sense that it has to obey to this equation here that we're going to build. And we have also to remember that organization can be destroyed. How? Well, in many ways. For example, the simplest, but the most complicated, and definitely it's not my cup of tea, is to add some non-linear terms, and you will get, for example, turbulence. No, I'm lazy. There is no room for turbulence in this course. In nature, it's full. But as soon as you add some non-linear terms, organization is destroyed. There is another way to destroy organization, is to create a disorder by, for example, scattering. Well, you were in Trieste yesterday. You have seen there were many clouds, thunderstorm, rain, and the light from the sun was scattered, blocked in some cases. But definitely the ray was bouncing on some water vapor molecules, scattered, 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 and you have diffusion. So actually you can take something that is ordered as a wave, like vibrations, into a solid, but when these vibrations are going to travel and they are going to look for many obstacles, that organization is going to be destroyed, and you can call it diffusion. And that's why, if you want, heat is starting as a wave, but it is so disordered by scattering that it's becoming a diffusion process. So you have a flow that is no more obeying the equation as before, but it's losing 1t, and you get diffusion. Okay, there are some exceptions to disordered systems that can go back to ordered. For example, if you add nonlinear terms and some additional disturbing phenomena like dispersion, well, magically, we're going to build what we call a soliton. But we're not going to study solitons in this course. Then there is another possibility, taking the right arm there, that if you take a solid like this bar, and you don't play with the heater here, and you want to study diffusion, but you lower it at very, very low temperatures, the vibrations of the molecules, beyond 0 Kelvin, of course, they are a little bit ordered, and you can study the single vibrations of phonons. And so you can study heat as a wave, but you have to go to very low temperatures. So that's the general scheme, but we're going to move just in this one, and that's enough. We're going to build the wave equation in very simple systems. We're going to use for the whole course the string as a sort of a skeleton of a course. Because if it is infinite, you can write this. If you add boundary conditions, you can create standing waves. So you decide the length of a string, and the energy has to bounce back and forth and to stand. And so we can also find some solutions to the wave equation. That's the simplest one. You like it. I like it. I love it. But are we sure that it is a useful one? Because you know, e2y something, it's sines and cosines. Nice. Thanks to Euler, we know that this is nothing else than sines and cosines. Is it enough? Because maybe on WED or Friday, we're going to ask, okay, what is the general solution of this equation here? It's not this one. This is a specific solution. It's a very polite one. It's very useful. Why? Well, because for lazy people like myself, taking derivatives of this is fine. Exponential is giving exponential. That's nice. But are we sure that we can use this one and forget about the others? Because actually, the most general solution of this equation is not this one. The most general is something like that. Whatever function that is polite enough to suffer from two derivatives in time and space joined by velocity is a solution of that equation. And this is called D'Alembert solution. It was a French mathematician and physicist at the time. There was not a big distinction between mathematics and physics. And he demonstrated in a very simple way why this is the general solution. Some details here. Well, usually, lazy people is saying, okay, thank you, Monsieur D'Alembert, but we prefer this one. And why we like it? Because it's simpler. But is it enough? Yes, thanks to another French mathematician that is called Joseph Fourier. And he demonstrated after the French Revolution that if you properly combine sines and cosine, you can write whatever. So, the funny thing here is that this is a specific form of this, and if you are smart enough, we can use it to build whatever function. Polite function. Okay? So that's why at the end of the story, we're going to use this. Now, just to go towards the end of this very chaotic introduction, let me ask you a question. What would you say to characterize this expression here, that is a plain harmonic wave, harmonic because we have EI, funny, thanks, Fourier and D'Alembert, but okay, who is going to tell me? What is going to tell me which kind of wave? Is it a sound wave? Is it a light wave?
Plane wave.
It's plane, because A is constant. But what is going to characterize if it is a sound or light or whatever?
A variable.
Which one?
X.
The speed?
Speed. And what is speed there? No, not alone. Omega and omega.
And K.
Omega and K. Because if you look at that form there, and if you divide by omega, or vice versa, velocity, please remember in this course, very basic things, but also let's remember every time to give a look to units. Omega, sorry, I'm polite because still we don't have defined these things there. But omega usually is frequency. Well, better is angular velocity. It's some radians over time. What about k? It will become wavelength. Wave number, I'm sorry. That is radians over distance. If you take omega over k, you get the velocity. So that's the first thing. Given a frequency, the related wavelength and together they build a velocity, they will tell it, okay, if the speed is about, today is 342 meters per second, that's a sound wave. If it is, let's say, 300,000 kilometers per second, it's a light wave in vacuum. But that's not enough. Because we have to remember that also the direction of a perturbation will be important. For example, sound waves are compressions and rarefactions. So phi, or the wave function, is expressing something in the same direction of the propagation. It's pushing and pulling, pushing and pulling. Light waves are transverse waves. So if the direction of propagation is x, vibration will occur on a plane perpendicular. So we have to remember also the polarization of a wave, if it is longitudinal or transverse. And this is what we're going to study. But just to relax at this moment now, let me show to you another website that I'm going to visit many times. You will have in the syllabus the links, I hope. And I want to show to you the animation that probably I will show to you more in this course. And I hope. Okay. Our first target is to understand this animation here. You could say, come on, it's easy. Well, that's a sound wave. No, it's not a sound wave. It's a representation of a sound wave. We're going to build it. So you can look at it and relax. Or be scared. But it's very nice. Because what is showing here is a set of particles that are building a system. It could be a gas. It could be the air in this room here. And unfortunately for you, I'm speaking. And what I'm causing here, if I am a very simple source, something that is oscillating with a given frequency and with a given amplitude, is that the set of particles is pushed and pulled, pushed and pulled. Why we are reacting? Because it's not visible, but it's not a set of free particles. It's a gas. N2O2, for example. There is a connection between N2 and the 2, that is the atmosphere, pretty much, that is putting molecules together. So they have tiny forces, but not zero forces. The reaction is that when I move part of a system, this perturbation will move throughout the system, causing energy to travel. You could say also mass is traveling. No. That's why Dr. Russell decided to focus the attention on two molecules, for example. Look at this one. It's moving, but it's oscillating around an equilibrium position. No sound, everything is quiet. Me speaking, okay. Look. Every single system, every single particle of this system is oscillating like an harmonic oscillator. But with a phase and an amplitude and a frequency that is dictated by the source. The collective motion, actually, is, if you give a look to this, to wavefronts that are traveling with a given speed. That's the wave. It's not the single particle. It's the collective motion that is built by the ordered motion of the particles. So mass is moving, but around the equilibrium position. There is not a flow of mass. It's not wind. Okay? In fluid dynamics, usually you study flow of mass and matter, but not in this case here. Energy is flowing, but not mass. Mass is oscillating. And you see, these are the waveforms. So this is what we're going to build. And these are sound waves. Why? Well, the first answer is that they are made by compressions and rarefactions. And if you give a look to the direction of propagation here along x, you will see that the motion of the particles is along that direction, longitudinal waves. But it's very different from this one. You can imagine this as a piece of a string looking with a lens that is a macroscopic lens. So you see the atoms of the string that are vibrating. Now energy is flowing along x again, but the motion is along y. It's transverse. Like EM waves, like, as we will see, shear waves. And now to show to you all the beautiful panoramic view of the other waves, well, we're not going to study this. Maybe in the seismological course, speaking about tsunamis. That's a beautiful wave, but the restoring force here is gravity. Usually these are the waves that you can admire going to the seashore. You can throw a stone or you can wait for some wind. And you know that Trieste has Bora. You know Bora? Oh, you have felt some Bora in the previous days, but you have to wait for the winter one. Okay. So gravity waves. What we're going to study are these ones. And these are really beautiful. These are Rayleigh waves. And Lord Rayleigh, I mentioned many people today. Hooke, Newton, D'Alembert, Fourier. And now it's the time of Lord Rayleigh. But actually the name was Sir William Strutt. He won the Nobel Prize for the discovery of armor, I guess. But it's also the father of many wave systems, like sound waves, and also seismological waves that are very important. We are using this for tomography, for seismic hazard, whatever. They are called Rayleigh waves. You see wave systems that are more complicated than longitudinal and transverse. We're going to build these ones. So this is another website that I will visit very frequently. And the first step will be in building this, that will be sound wave equation, trying to understand the solutions, and try to understand this animation here. What's next? Well, just to, let's see if it is on. A couple of seconds. Just the final. Okay. We have to wait for Java to wake up. Oh my god. Okay. Just to tell you one thing. Waves, number of volts. Okay. You see the? Yes, you do see it. You like it? Let's be first topic. First topic is very boring. Harmonic oscillator. What have I done here? Okay. Let's move. Okay. Next step. Next step. Oops. Well, I can increase it. Now, when I give energy to the system from one side, no energy will travel. At the end of the system, it will come back. That's the birth of a wave. Just considering coupled oscillators. And of course, if you consider an infinite distribution of these ones, we're going to build a continuous string. And that's why, just to end this prequel here, that's another important brick in the wave wall. Do you see it? Yes. Now I can plug it, and that's a system with progressive waves in a string. Well, the funny thing is that that motion can be built, is actually built, summing the normal modes of the system, like this one, like this one, like this one. So if I move on these ones, I can highlight the contribution of those modes. I can play with them. Thanks to Joseph Baptiste, and he had another name that I don't remember now, Fourier, we can play with this, considering the single modes, summing them, and to build whatever. That's why we can use harmonic plane waves, because with those we can build whatever. So for example, if I plug the string at the center, what I'm going to excite mainly will be the first mode. That's the most important contribution, as you can see. But if I play it in another place, other modes will enter. And the modal analysis is one of the most important things that one can study to understand linear systems. We can try to apply this concept to the Earth, or in a simple fashion to a building, to a stable, to a string. Okay? The principle is the same. But if you are a flute player, it will be more important to study the modes of a air column. Different games that can be used to play with waves. Okay. Now, time for animation is finished, and we have to move to the next very boring lecture that is starting here. Now, one warning. I will try now to be relatively fast. And we're going to stop in half an hour, then we're going to start again in the afternoon. But one word. Since this first lecture is very simple, I will skip some slides. But, they do contain some exercises, but you can do it by yourself. Very simple. Another general announcement for this course. During the course, when we will be able to tackle with some arguments, I will assign to you some homework. Today, they are not official. Do the exercise that I will skip, and I will give to you a beautiful paper made by Roelsnieder, that is a friend of mine. He is a very good theoretical geophysicist, whose paper is called, it's made by 2 pages, I think no formula if I remember correctly, it is called What is a Wave? And it's exactly the paper that I've been using in the last years to build the first lecture that we have seen together. What is a wave? So first homework is very nice, not official, to read the paper that I'm going to send to you by email, and to give a look to the examples in this lecture. They are very simple. Let me tell you one other thing. At the end of the course, you will have an exam. I hate exams. I know that you hate exams. But we have to do it. According to the last year's experience, it seems that you, not you, but the different generation of students, they do prefer written exams. Well, you have to know that sooner or later, you will have oral exams. And sooner or later, you will give oral presentations to introduce yourself and to explain your work. So, it's time to begin to use oral, but wave physics exam will be written. Theoretical seismology exam will be oral. Okay? So you will have time to tune about these things. And the final evaluation, I hate evaluations, and I hate evaluations, will be a sort of a mixture between what you're going to do in your homework, a very tiny percentage, and what you're going to do in the written exam. Okay? to be 30, usually it is 30% and 70%, but it's not rigorous, okay? To your favor. So, for today, and maybe for the first 3 lectures, just unofficial homework, but I will give to you 3 set of homework that will be the sort of the official ones. You are going to reply, but I will tell you again how to act. You will prepare a PDF with solutions, and you are going to send it back to me by using your email. But that will be in the future, okay? So for today, just informal homework. So let's start. I will be fast with these slides because I'm sure that all of you already know many things here. For example, what is an oscillation? Well, oscillation or vibration, it depends. Physicists we do prefer to use the term oscillation. Some engineers, they do prefer vibration. The common feature that is beyond these 2 terms is that usually we are referring to periodic vibrations and oscillation. And the typical example is this. Well, it's a picture, but actually it's a physical system. Like myself playing in a silly way with this. So, we have a system, a physical system. The next step is to build a model. For example, that's, you can call it engineering or not, or a physical model. So, from a system to a model. That's not a mathematical pendulum. It's called a physical pendulum, but it's still a model. Well, you know that actually it can be solved using the center of mass and this distance exactly as the pendulum. By the way, we can write the dynamics, and then we can get, after modeling, a differential equation with dynamics. After some cleaning, like putting away, throwing away all the non-linear terms, small angles, we get a mathematical model. So we can knock the mathematician's door and ask, can you give us, please, the solutions? Yes. And that's why, after the physical law and modeling, we have a solution. Okay? This is what we're going to do, starting from scratch. We have also to remember, after adding maths, that every time that we are going to use our model, we have to take care about the most important features. The first ones are, for example, in the case of the mechanical system, is inertia. Newton, and if you prefer, before Galileo Galilei. Good. Then the restoring force, Robert Hooke, in the case of elasticity. And then we have also to remember to add some realistic component, like dissipation. And the typical example that is used in vibrators to deal with something that is removing energy, like damping, is to use some strange thing where the vibration is occurring with some viscosity. And what is funny is that the typical ingredient that we add to the system to deal in a very simple and elegant way with dissipation is to add a Newtonian fluid, still Isaac Newton. He is still there. Okay, once we do that, yes?
How does inertia cause kinetic energy?
In the sense that, in a very simple example of a spring and a mass, now we have 2 energies. Okay? And the other one is. Now, if you give a look to this, kinetic energy is related to M. Well, potential energy is related to the force. So if you want the 2 parts of the system, one is taking care about potential, the other one is about kinetic. That's the idea. Of course, they mix together and they combine with the conservation of energy. And the coupling is here, because as we are going to find, the frequency of the system is related to both. So if you wanted just a very simple sketch here, because what we're going to build today is a linear oscillator damped, and then we're going to force it. So mass, stiffness, length. These are the three ingredients that we can use to build our system. The first one, sorry, let me skip this one. Resonance, I told you, that's the forcing. This is what we're going to do. And now it's time to, we already discussed this. Let me skip this simple thing here. Okay, that's the starting. Now we ask to Sir Robert Hooke to help us. If the system is in equilibrium and no one is touching it, it will stay forever in equilibrium. Nice. We are lazy but not that lazy. We have to try to apply some perturbation. For example, we can compress it. And immediately we get a reaction. Because the restoring force, the spring, is trying to push it back. Or maybe we can stretch it. And immediately we feel a pull. How much? Well, that was not trivial, but when Robert Hooke solved this problem, he was studying the direction of the force, measuring from an equilibrium point, so measuring the distance from the equilibrium, putting the things together, and everything is related to what is called a spring constant. Hooke's law. Funny thing is this one. It was not that long time ago. So it's quite relatively recent law. What is funny is that at that time there were no scientific publications, as we intend them now, peer review with some copyright, something like that. So usually scientists, they were publishing their results using acronyms or anagrams. And so he was publishing this. Now, that's not comprehensible, but actually it's the anagram of ut tensio sic vis. That's Latin. That means, okay, as soon as I perturb, I feel a force. If I apply a tension, I feel a force. Okay, so that's the historical background of that force. Now, before to proceed, we can go here. Let's couple Robert Hooke with Isaac Newton. Because if you have a force, immediately we have acceleration. So you can write acceleration as the second derivative respect to time. Okay, high school physics. You put them together, you can put them together, and you get, let's see, this. Now, sorry for being so trivial here, but what we have is a dynamic equation that is a second order differential equation that is linear. Why? Because the restoring force is linear. It's in one variable. Why? Because our universe is a point connected to a spring. So one variable, dependent, one independent variable that is time, two parameters that are building the system, k and m, that's the end. So linear, second order, blah, blah, blah. Okay, what can we say with this? The acronym that I'm using is SHM, simple harmonic motion. Why harmonic? Well, you know the story. The point is that the solution of this differential equation, it's, okay, let's try to think about it. It's a second order differential equation. So its general solution should be a linear combination of two independent solutions that are actually an orthonormal base of this system, sines and cosines. We're lucky. That's a simple one. The solution will contain something that we're going to call a period. And now let's put the base for some important units here. Period is measured in seconds. Okay. The reverse of the period, it's called frequency. It means how many cycles is doing in 1 second. It's measured in hertz. And in acoustic sense seismology, hertz is one of the most important units that we're going to use. Okay, other units here, because the solution that we're going to write will have also an amplitude, the amplitude of oscillation. That will be measured in meters in this system here. What about this one? Maybe angles are better, but we can convert angles thanks to the length of a pendulum with distances. Okay, so let's remember units. Now, what about the mass? Well, okay, kilograms. We're using international system units. What about K? Yes, but what about the units? Uh-oh.
Per meter.
What?
Newton per meter.
Are we sure? Maybe you're right. Oh, it's here. What is a Newton? So what? In basic units? Okay, let's remember, okay? Because we have to use 3 units. Nice. The only one new unit here is this. Where is Hertz here? Well, actually, it's here. Because if you take the units of a force, then you take the units of K, and if you divide them by M, you will see that a period will appear, actually the square of a period. So actually, what is going to decide the periodicity of the system is the combination of K and M. It seems really silly what I'm saying to you, but remember that the early days of instrumental seismology, instruments were like this. And within this year, you're going to visit the giant cave that is, let's say, 5 kilometers from here, where there is one of the longest pendulums in the world. It's pretty much 100 meters. It would be nice, it would be beautiful, but can you imagine to make a seismological campaign with instruments that are 100 meters long? No. So, one interesting feature about pendula is that what we're going to find, thanks to Galileo, is that their period will be related, we're going to find this, by the length and gravity. Now, if you want to study 100 seconds here, you need pretty much here 100 meters. Not easy. Maybe we can use a system with a spring and a mass. And you will see, I was writing it, but the period maybe we can use this one. Now, wait a second. Can you imagine to measure 100 seconds with that system? You would need a very large mass and a very small K. That system is going to break as soon as some important vibration is going to occur, because you have a weak spring with a large mass. So you do understand that beyond and behind these simple features here, there are some technical problems that we are going to look at during the seismological course. Now, high school plots. Because actually what we have in mind as a solution of that equation is this. So you have a spring that is oscillating back and forth, you connect with the pen, and you have a seismogram, a very simple one, like that one. Okay, how to write it? Please remember that since that is a second order equation, you need 2 constants of motion. What does it mean? The amplitude and the phase. There is another way to write it as A times cosine of omega t plus B sine of omega t. It's the same. It's the same. What is important is that we have every time to fix two constants of motion. Amplitude and phase, or how much cosine, how much sine. For example, typical exercise of a wave physics exam. Let's imagine to have a pendulum, and the initial condition is this one, I release it. Okay. Which function would you use in this case here? I'm trying to exaggerate, okay? You start from a position that is not the equilibrium, right?
Cosine.
So it's going to be, okay. On the other side, if I start from here and I give some velocity, it will start from 0. That will be a sine. So, please do remember that the two constants of motion, also for this very simple system here, are decided by initial conditions. And please do remember that A and delta are decided by initial conditions. Omega is not, is decided by the system. Okay? How to find it? Well, it's time for some boring algebra before lunch. And can we show that this expression is a solution? Well, you know, a mathematician would do the opposite. It's going to study the differential equation and to look for the solutions. A physicist, on the other side, is looking for some Ansatz, technically it's German, but some trial solutions, and to see if they work. So we have that in mind. Can we demonstrate that it is a solution? Well, let's take the derivatives. Okay? Very simple ones. You compute velocity, and now, please do remember since now the units. If x is displacement, meters, that's meters per second. Meters per second squared, it's an acceleration. Please give a look. These are total derivatives. Why? Of course, we have just one point. We have nothing else in the world. The only variable that is changing here is time. So it's a total derivative respect to time. Okay. So acceleration is this. Good. Now, let's give a look to the other part of the game here. Let's put them together. And we can say, yes, this is a solution if omega is the square root of k over m. In other words, we can take this equation, we call k over m omega 0 square, we put it there, and we have a solution. Wait a second. What are the units of omega?
Radian per second.
And now, I'm very unpolar, because I'm asking to you another question. Yes, you're right. Why radians?
Because it's angular.
Do you see angles here? I'm joking, sorry, but we're not speaking about pendula. Now we have a mass that is oscillating up and down, back and forth. There are no angles here. But very correctly, we have to say that omega is not hertz. Actually, its units is radians over seconds. Well, you know why? Because the argument of any trigonometric function should be a pure number. So actually, if we're using radians, this has to be expressed in radians. And if we have time here, that has to be radians over seconds. So you're right. But it's so strange that we don't have circles here. That actually, and this is another important property, actually, so, okay, this is the, oh my god, no, still is where 4 minutes. But please do remember that in general, To find A and delta, amplitude and phase, or if you want the coefficients of sine and cosine, you need to take the initial conditions. Which ones? Well, we're working with acceleration. We have to fix velocity and displacement at time equals 0. Actually, those two conditions, so x0 and v0, will decide A and delta. Okay, and then we can find also that the period is related to omega. Good. And so, we have this very basic, very simple condition, but we have a period that is the reciprocal of the frequency, and it is related to omega. Hertz, seconds, radians over seconds. And in this system here, everything is decided by K and M. It's called the natural frequency of the system. What's next? That's important. For example, in one of the exercises of the wave physics exam, maybe I will ask you, given a pendulum with these initial conditions, please write the time history. Remember that for time history, usually we intend displacement, like the top. Units, meters, or angles, if we are dealing with pendulum. But if we start with this, it will be a cosine. Okay? When you compute the velocity, it means that we are going to take a derivative of displacement respect to time. We have only one velocity here, this one. And you see, it has a different amplitude because now omega is coming out. Okay? And the phase is different. When displacement is maximum, velocity is 0. Let's imagine this oscillation. When velocity is maximum, displacement is 0, and vice versa. Potential, kinetic, potential. Okay? And the game is running again forever. Acceleration, different amplitude and different phase. One word immediately. This velocity here is not the velocity of a wave. We don't have waves here. We have just an oscillation. It's the velocity of vibration. Okay? Same units, but it's something different. It's the total derivative of displacement respect to time. And I want to stop here with this one, with an animation. Because actually, why radians? Well, if you take the very simple example, typical of high school physics, of a circular motion with constant angular velocity, everything is fine, everything is constant. And you consider the motion of that mass around its center with a given angular velocity, well, you can write the equations of motion, of course. And the angles will be described by an angular velocity times time plus an initial, oh, sorry, that should be initial delta. Okay. Now, let's imagine this boring motion, and let's imagine to decompose along x and y. You will have immediately, two harmonic oscillations. One in cosine, the other in sine. And of course, this is angular velocity that is related to tangential velocity divided by the amplitude. And what I want to say, that if you take the two positions, you will have cosine and sine. So that's why, if you want, there is omega there in terms of radians, because if you consider just this, and now we have an angle, okay? And if you decompose it, you will have the physical meaning of a simple harmonic motion in terms of the motion along the two axes. Let me close this first part with this animation here. Okay. variable. So you see on the left, we have a mass that is running with the tangential velocity and the constant angular velocity, omega. And those units are radians over second. It's an angular velocity. Now, if you take the x and the y, you will see their phase is different, cosine and sine. Maximum amplitude is the same. And, of course, if you take them by alone themselves, they are two SHA. Okay, what we are going to do in the afternoon is to make some energetic considerations, and then we're going to study the pendulum.
So, what is the information that we can extract from phase? Phase of the wave.
Usually, actually, from your question, and also it's very intuitive, we try to forget phase. Amplitude is important, what about phase? And it's real. Well, let me say, phase is the initial angle, in this case here. Zero phase, and then you take this, okay, and you have a sine. So you can call this motion as a sine motion with zero phase. Or you can take this, an initial phase, and you have the sine with the phase, now it's cosine. So actually, phase and amplitude are containing the same information together. And it is the initial condition. So the initial condition is containing two things here. How much in terms of amplitude, because I can do this, and that's A. And how much in terms of phase. I can start from initial phase 0, and like that. So, what is the information of phase? It's still an important information about the initial condition. What I want to say is that, and let me close here because I don't want to steal time, is that once you have this equation, and if someone is going to ask you, what is the general solution of that equation? Well, you have to write this. Let me use not A, but A and A. Full stop. Now, that's the general solution. Now there is no phase. There is how much A, how much B. And it's a linear combination of two independent solutions. That's at the base of that differential operator, this one. Okay? Now there is another way to write it. Now, here you have amplitude and phase. So when you're saying what is phase? Well, physically, it's the initial angle. And that's the initial amplitude. But if you write it in this way, A and B, you see they are the same. So there is not hierarchy in A and B. Both are related to initial conditions. But let me tell you one thing, that when you study acoustics, human acoustics, not physical acoustics, but human acoustics, you have to know that, for example, our auditory system is not sensitive to phase. So you can take a sound and change. I will show to you later. I will let you hear later. We will spend a very short lecture about acoustics, and you will hear a sound. Let me do it now, and then we will. And then we close. Now you are going to listen, I hope, a cosine and a sine. That's a 220, very boring. Now you are going to listen a cosine. No difference, okay? But they are different. Now let's take, it will not be nice. Or, that's not nice. Let me change the phase. For example, you see here it is written in terms of sine and cosines, now in amplitude and phase. Now I'm going to change a phase. The time signal is changing. Look, it's changing a lot, right? Do you agree with me? But the sound is not. So if you want, in the physical acoustics world, phase is important as amplitude. In human acoustics, it's not. But you have to study it. Okay, guys, let's meet at 2, right? We are going to continue. Okay. I think I will leave. And I hope to have some news about the Moodle website.